Hello and welcome back to the Energy Onion Energy Systems Engineer Training Certification, Chapter 4. You'll recall we have seen through our introductory chapter, Green Buildings, LEED, Energy Star. We've done some math. Wasn't that fun? We've looked at utility bills, energy accounting. Chapter 2, we saw lighting, and in Chapter 3, we looked at HVAC and thermal energy storage. Now we consider the building envelope. As we have started other chapters, we'll start the building envelope chapter with some definition, followed on with other building envelope considerations, and we'll spend a majority of our time in solar heat and glazing. As we'll say later, it's not because glazing or windows are more important than the other building envelope considerations, only that the opportunity to improve glazing is more apparent, more available, and more retrofittable. The definition of the building envelope includes such components as the floor, the walls, the windows, doors, any penetration like an exhaust stack or a vent, and of course the roof. As we consider performance factors, we'll consider, of course, what you know to be true, and that is that the design of the component will affect its performance. But as will the exposure, whether it's on the north, the south, the east, the west, or the roof. Also, performance of the building envelope is impacted by the materials they're constructed of. You can imagine an aluminum frame with a higher thermal conductivity will conduct heat from the outside to the inside more than a wood frame or a vinyl frame. Of course, the workmanship and the quality of the component affects the performance. The commissioning, the process, whether we use it in the context of the building envelope or any other energy engineering system, the commissioning, that is the process that you say the building is ready for battle. It's commissioned, as in a ship. Also, the maintenance affects the performance of any building envelope component. And lastly, the change in use. If you built a building or integrated a building envelope and the use had a specific purpose, but it was repurposed for a different use, that new use can affect the performance of the building envelope. These three terms are things you're going to have to learn and be familiar with as we go through the methods of heat transfer. You'll see them again and again throughout this chapter, and that is the heat transfer by radiation, by convection, and by conduction. And adjacent to the heat transfer method is a typical glass or glazing solution to that type of heat transfer. If you have a radiative heat transfer problem, you need window film or coated glass to solve that problem. Another pane of glass, as you'll see in the next slide, won't help. If you have a convective heat transfer problem, you need window coverings to prevent that. If you have a conductive heat transfer problem, you need insulated glass, 2 panes of glass, or gas-filled glass. These are complementary solutions to different heat transfer problems. The next thing you'll see here is this little equation. You'll see it later. What this says, this conductive heat transfer equation says that we need to consider in the conduction, in H, the material itself, the conductivity of the material itself. That's the little K. We need to consider the area across which heat is conducting. And we need to consider the temperature difference. Very key in considering conductive heat transfer. What's the difference between the two sides across which heat is conducting? And then X, the thickness of the material across which heat is conducting. Convection and conduction are more intuitive than radiation. You understand those. But what of radiation? What of this third method of heat transfer, and what can you do to stop it? Let's consider, for example, you have a single pane of clear glass, and you have a high solar heat gain. It's hot, and all the heat seems to come right through the glass. So let's say you put in dual pane windows. Well, what this graph is it shows the transmission through single pane clear glass. So you can see the reduction from the glass is somewhere around 10%. So if you put in another pane of glass, you might get down to 80% heat transfer by radiation. So this graph shows that the solution to radiative heat gain cannot be just more glass. Convection and convective heat transfer is pictured in the next two slides. This is a simple picture of two different modes of convective heat transfer. The first is air coming from the outside in, leaks into the building from the outside, or out of the building from the inside. Those are both convective heat transfer. But in addition, shown here is convective transfer between interior spaces. Of course, if you have interior spaces that are conditioned to different set points, that transfer can cause those two air conditioning systems to battle each other. These are both, whether from outside in, inside out, and between interior spaces, both are convective heat transfer. But this picture of convective heat transfer shows a little more insidious heat transfer. If there's a gap in a window or a gap in a door, you'll feel it. But what if there's a collection of small gaps that you can't feel and you can't see because they're between the outside facade, in this case maybe a brick veneer, and the exterior sheathing or cavity? There's a little gap there, and the gap in its area is huge. The gaps themselves are small, so a lot of these small gaps can create a substantial unintended influx of outside air, an increase in negative pressure. So you see from this picture, you can get air quality problems in addition to the unintended negative pressure between the exterior and interior spaces. And lastly, in convection, is just a picture to show what convection might look like. It might not look like or feel like a breeze flowing through a space. In this case, what you see is a nice, clean, finished space below the ceiling grid. But above the ceiling grid, you see unfinished drywall, and you see blown in insulation, and you see what looks like maybe it used to be some pink fiberglass insulation. But it's not pink anymore. It's black. And it's not uniformly black. There's a centrality to it. It's black in the corner. What this shows you is that air has been flowing out of this conditioned space through this insulation into either another space or the outside. We don't know from this picture. But what we know is there's unintended air transfer through this insulation. And instead of acting like insulation, it's acting like a filter. The next thing we'll look at here is a little more specificity around this idea of conduction. And the reason is, as we look at building envelope, the conduction and the radiation are going to be where we focus our attention. We looked at the graph earlier on radiation. Let's look at conduction. What this says is, as it said earlier in that smaller version of the same equation, is that the heat conduction is equal to some constant, the conductivity of the material, times the area across which the heat is conducting, times the temperature difference divided by the thickness. But not all of these terms are the same, are of equal weight. Take, for example, the thermal conductivity. The property of the material is going to be important as we consider conductive heat loss. The temperature difference. This is going to be a major consideration as we consider whether the radiative heat transfer or conductive heat transfer predominates. And the next consideration is the thickness. If a component is twice as thick, everything else being equal, the heat conduction will be half. One of the components of conductive heat transfer we looked at the thermal conductivity earlier. Well, the R value is the thermal resistivity. The R is resistivity. It's the inverse of the conductivity. So since we consider R value most frequently when we're considering the thermal performance or the conductive thermal performance of a wall, for example, well, let's look at how R value is calculated. A simple R value in this example would say the outside air. You see the brick and the drywall there. Let's say the outside air has some R value, and the inside air has a different R value. You have brick, fiberglass insulation, and drywall that all have some R value. The simple calculation is just add them up. If you have that configuration, indeed you can just add them up. In the, quotes, real world, however, you don't have an example like that. Looking at this picture, probably the first thing you noticed are these yellow rectangles with the X in them. Well, that's the symbol used in architecture for the end of a board. So here we're using it as an example of the end of a 2x4 stud. So there are studs in these walls with this insulation. So how do you account for that? Well, what you have to do when calculating R value in the real world is first consider that the R, the resistivity, is 1 over, as we said earlier, the conductivity. The real number we use when calculating building envelope and wall or window thermal conductivity is not K as in the earlier example, it's U. And the thermal conductivity of the wall is equal to the conductivity of the cavity plus the frame. Those are two different types. So you have to look at what proportion of this figure is cavity, drywall, insulation, brick. And what proportion of this picture is frame, drywall, stud, brick. Proportion those, and you see that with the summation of the R values, the reciprocal summation, and you add them up. So on the previous example, we had an R value of 12.9. But indeed, there is a conduction of heat across this 2x4 that is greater than the insulation. You can tell that from the R value themselves, insulation being 11, the stud wall being 3.59. So this accounts for not total complexity in a real life situation, but more real life than without the studs. Now that we have seen some of the slides we've seen, we've been able to give you a vision, a context for that term. For example, now that you've seen what heat transfer looks like in convection, conduction, radiation, and you've seen R versus U and resistivity and conductivity or heat transfer coefficient, now we'll look at emissivity. Emissivity is technically the ability of a surface to emit heat by radiation. You hear of low E glass. And typically, emissivity is inversely related to reflectivity. But emissivity is, as you hear of low E glass, know now that the E is for emissivity, not for low energy glass. And leaks. Wow, where are we if we're defining what a leak is? But understand it's included in definitions to highlight that a building leak could be building related, as we saw in the convective heat losses and the infiltration. Those were leaks. But we will define it so that you know leaks also can include procedural problems such as open doors. The solar heat gain coefficient, it is similar in its description to the shading coefficient. And they're both measures of how well something, often glass, blocks heat from the sun. The coefficient of solar heat gain. A thermal break is where, let's say you have something that has a high thermal conductivity. If you can put something on one side of that to mitigate that high thermal heat transfer, that's called a thermal break. I mentioned earlier that we're going to spend a good chunk of our building envelope time on glass and glazing. And the reason isn't because they're more important, glass, or the way glass is put together. It's not more important than other building envelope components. But the readily available improvements to glass and glazing, be it window replacement or window film, these readily available solutions are why we camp out here. First, on types of glass and glazing, we'll discuss glass types. The glass itself. The glass can be annealed. Annealed float glass is what you might consider regular glass, plate glass. The glass can be heat treated or chemically strengthened or tempered. And you do that for a couple different reasons. You can do it because you want the glass to be stronger for some performance characteristic, or you do it so that it will break more safely. Take a look at the two pictures on the bottom. The one on the left is how annealed glass breaks. You see those long shards of glass. Tempered glass breaks like the picture on the right. Because of the built-in stresses of the tempering process, the glass breaks into little tiny bits. And then any of these glass types themselves can be either clear or the glass can be tinted in some fashion. The glass itself can be colored. And then these glasses can have surface coatings applied, low E or low E squared, or a reflective, shiny surface coating. Then these glass types can be constructed in a manner of different ways. First is the number of panes. The most obvious is it single pane, dual pane, triple pane. And then there's a construction that involves suspended films, where a film is suspended between the two panes of glass, offering UV protection, infrared protection, whatever it is you're trying to do. Instead of suspending a film with an air gap on either side, you can laminate two pieces of glass together using a component called PVB. And what that allows you to do is, once it is applied properly and processed properly, it's clear, so you can see through it, but it provides strength to the glass. And lamination is how your car windshield is made. If you've noticed, your car windshield breaks differently than the side windows, because the side windows are just tempered glass and the windshield is laminated glass. Glass and plastic or polycarbonate can be multi-layered to provide bullet or blast resistant glazing. The panes, if you say for example have a dual pane window, that space between the panes can be filled with a gas, argon, krypton. The glass surface can be textured, and lastly, there can be a wire applied between two laminated pieces of glass. And that wired lamination is not to provide safety, but to provide for protection in the case of a fire. Here's a construction of a window that has a low E coating, the low E being pictured by a brown coating. And what the low E does is it is a low emissivity coating. It has a low ability to re-radiate heat. This next picture is an example of the suspended film we talked about. In this case, there are two films suspended between these two panes of glass. This is called a quad glass or super glass. And indeed, with this dual pane window and 2 suspended films that have a special coating on them, you can get windows that perform as insulation as efficiently as a 2x4 stud wall. We're now going to look at window film as another way to improve building envelope as it pertains to glass and glazing. Window film is constructed on a base of PET, polyethylene terephthalate, and on one side is a scratch-resistant coating. That's so the film can be installed without scratching and cleaned without scratching. On the other side of the film is a mounting adhesive built into the film as it comes from the factory. This mounting adhesive is water activated, as the jargon goes, so it can be installed in the field and be crystal clear. On top of the mounting adhesive is the disposable release liner that upon installation you peel the release liner back, spray the mounting adhesive with water, spray the window with water, and the film is applied in that fashion. One thing we did not say, this is a simplification. Indeed, that what we called a PET backbone, it could be clear plastic, it could have metal on it or dyes in it to change the performance or appearance of the film. That PET backbone, it could be one single ply of PET, it could be 3 or 4 plies laminated together. So it's a simplification, but you see the componentry of window film construction and how it's applied and protected. The purpose of this slide is to introduce the terms on the right. We're not going to define them anymore because in this Energy Systems Engineering certification, these are not energy system solutions. These are window film solutions that you can get maybe for free, maybe for very little, if it's an upgrade from a window film solution you're getting for energy conservation. So let's take some time and look at the terms on the left: solar control, U value, R value, emissivity, as they pertain generically to replacement windows, window film. These are window solutions terms. So we have presented here, this happens to be a window film example, but this could be the same for a tinted glass example, and that is, as it pertains to glass and glazing, what are some important terms we're going to use? The what is total solar energy. What is that? Visible light, ultraviolet light, infrared. That's the what. The how are those variables represented? Each one of those, total solar energy, visible light, ultraviolet, infrared, every one of them, 100% is either transmitted, reflected, or absorbed. And that's an important distinction, because as you then look at window solutions, be it windows or window film, you need to know whether that energy in the list of what is being reflected, absorbed, or transmitted to have a full understanding of what the improvement is. Look, for example, at the clear glass at the top. 100% of the energy hitting the glass. For quarter-inch clear glass, 7% is reflected, 9% is absorbed, and 84% of the total solar energy is transmitted. Change that around and either add a silver 15 type window film or consider this that kind of reflective glass. Either one, with 100% of total solar energy again impinging on the glass. In this case, you have 44% reflected, 46% absorbed, and 10% transmitted. With the earlier definition of transmission, absorption, reflection, I wanted to give you a picture of what that looks like. Again, because it's important to know. Say, for example, you have transmission of 84%, as in the quarter-inch single pane of glass. Let's say you cut that transmission to 10%. Would it be different? Would the net effect be different if that 74% difference was reflected back outside or absorbed by the glass? Of course it would be different for two reasons. One is, if it's absorbed, some of it will re-radiate into the room. If it's reflected, it's outside. So reflection with respect to heat rejection is more efficient. In addition, absorption can cause thermal stress fractures. So let's say you have a house at elevation in Denver, Colorado, and the house inside is 68 degrees and outside it's 10 degrees Fahrenheit. The sun comes up, heats up the top of the window, the bottom's in the shade. You can have an uneven distribution of heat. Now understand, glass doesn't break because it got too hot. It was made at over 1,000 degrees. It breaks because it's unevenly hot. So for that reason, a highly absorbing window or window and film combination will perform differently, even to the potential of breaking if it's not specified properly. So what this graph shows is that law, that reflection plus absorption plus transmission equals 100%. So let's look at this graph in its detail as wavelength sections. First, let's look from 0.3 to 0.4 microns. That's 300 to 400 nanometers. What you see is the transmission in this ultraviolet region is about 0. So you'll see window films in this example that have 99+% ultraviolet rejection. How is that ultraviolet being rejected? Well, you can see from the gray line it's being absorbed. In this case, the energy of ultraviolet is not as high, so absorbing all of that energy does not cause glass breakage concern. Let's look at the visible. In the visible, we have 70-some% transmission. So in the visible transmission, if you look through this glass, it looks very clear. What about the visible reflection? The reflection is something under 10%, visible being from 0.4 to 0.7 microns, 400 to 700 nanometers. And then as you get off to the right of 0.7 into the infrared, now you see the infrared reflection is very high. So what you can see from this graph is this is a film that has virtually no UV transmission. It blocks it all. It looks clear, and it blocks heat through reflection instead of absorption. These next two slides, because this is the Energy Systems Engineering course, are to put in context what we've been referring to as the UV, the visible, the near-infrared wavelengths. And what you see on this graph is their relative solar energy intensity. So indeed, you can calculate total solar energy rejection using the proportional rejection of UV, visible, infrared, and their proportional energy. You see here why I said earlier, UV absorption, 100% UV absorption does not cause glass breakage, whereas maybe 55% total solar energy or absorption can cause glass breakage. So where does this UV, visible, and infrared fit in the broader electromagnetic spectrum? From this graph you can see that all the way from gamma rays through X-rays, and then in the middle there, the ultraviolet, visible, and infrared we've been looking at, through microwaves, radio waves that their radio wavelength is 1 meter long. So what you can see here is the visible is a small part of the overall electromagnetic spectrum, and you can see an example of the relative sizes of those wavelengths. The next topic is the topic of emissivity. We looked at a low E window construction, and we referred to it a little bit, and we defined it in the beginning But emissivity is the ability of a body to re-radiate heat. And what we show on this graph is the difference in low E and a typical IR selective window or film. And the low E, again, does not stand for low energy, it stands for low emissivity. And what it says is that in the very, very long wavelength, over 2.5 microns, the low E has a very high infrared reflectivity, a low emissivity. Compare that to, in this infrared selective film, the blue line, you can see that in the short wavelength infrared, which is not the heat you generate in your house in the winter, it's the heat that comes through your windows in the summer, you can see the transmission of that infrared from 0.7 to 1.5 microns. That transmission is much lower. Pay attention to this graph. This is why, if you live in a warm climate, as I do in Phoenix, this is why even though you have, quote, low E windows, you still have too much heat coming through the windows, because low E blocks a different type, a different wavelength of infrared versus an infrared selective glass or film. I've been referring on a few graphs and in terminology to an infrared selective coating or film. Indeed, this could be an infrared selective coating on glass or an applied film. The graph looks the same. And I've been comparing it to emissivity and other things. What I want to do here is compare it to a conventional film window tint or a conventional tinted glass and show you how it is that with today's technology you can have a clear film that blocks over half the heat. Starting with the transmission, the dark blue, solid blue line versus the dashed blue line, the two transmission lines. You see the transmission in the visible for the IR selective film is over 70%. It's very clear. It's as clear as the windshield on your car. Versus the transmission of the conventional film, if you integrate under that curve between 0.4 and 0.7, this conventional film has about 50%, 52% transmission. And then looking in the infrared, 0.7 to 1.5 microns, the transmission in the infrared selective film is much lower than the transmission for the conventional film or glass. Likewise, look at the reflective lines. The solid orange line is the IR selective reflection. The dashed orange line is the conventional reflection. Well, what you see first is the appearance and visual from 0.4 to 0.7. The conventional film is much shinier. 20-something% visible light reflection. Versus the IR selective film or glass, reflectivity is less than 10%. As you go into the infrared reflection, they're both quite similar. I would like to provide pictures of both a IR selective glass and IR selective film. However, the IR selective glass, the coating's applied in a factory under vacuum. You can't see it. For the film, they do the same thing in a vacuum. They apply the coating, the exact same type of coating, to film. So I thought I'd show you a picture of what that film looks like on glass. And indeed, it's hard to tell, other than where the mounting solution bubbles are being squeegeed out, it's hard to tell where the film has been applied. This is an example of an IR selective coating, IR selective window film that could be applied to just the west side, or just the third floor, or just one office to improve the building envelope. The last and summary slide for glass and glazing is that, again, whether it is film or replacement glass, whatever the solution is for glass and glazing, you have to consider performance and appearance. Take, for example, the solar heat gain coefficient. We define that as the ability of a building envelope component to reduce solar heat gain. In this case, the IR selective window or film has a solar heat gain coefficient of 44%, identical to the conventional one. The difference comes in as you consider appearance, visible light transmission, and visible light reflection. We could make the opposite case as well. We could provide a window or film that had identical appearance as a conventional window or film, but then the difference would be in the performance. So make sure as you consider windows or film as a solution to a building envelope problem that you consider the performance characteristics and the appearance. And of course, we highly recommend installing samples, because a sample on a piece of glass in a conference room is not enough to make a decision about an office building. You need to see how it looks on your building. Although we don't present every building envelope component and how it can be evaluated, and we focus primarily on the windows, the glass and glazing, we do present the building load coefficient. An annual heating energy use, and for a building whose heating is dominated by envelope losses, can be estimated using this building load coefficient method. It's the ability of your building to reflect and react to load and the cost of that energy. With the building load coefficient being defined as fuel consumption divided by degree days minus base energy load, you can plot your fuel consumption by degree days. Degree days is a calculation that you can do based on weather data. And if you plot your fuel consumption by degree days and interpolate that with a straight line, the slope of that line is your building load coefficient, and the y-intercept of that line is your base energy. And this is a valuable exercise to see the performance of your building envelope. In summary, we have defined the building envelope as any component, including floors, walls, windows, doors, any penetration, or the roof, that provides separation between the inside and the outside for the purpose of controlling the temperature, the noise, air quality, moisture, or any other of these cross-boundary variables. We considered performance factors as the design, exposure, construction materials, workmanship, commissioning, maintenance, and changes in use. We focused on the ability to leverage technology in glass and glazing to improve building envelope, and finished with the back of the envelope calculation of building load coefficient.